Good afternoon. Yeah, so I can shout also, no problem. That's what teachers do in the class. So good afternoon, and who can be happier than me when a corrosion workshop is organized and planned for the future corrosion research. Thanks to the organizers, and more so, Dr. Shyam Sundar, Mr. Umesh, and the other people involved in the aerospace department. I'm eternally grateful for these people for really seeing that corrosion is an important topic. Thank you very much. So I would like to touch upon, I really don't know what to talk, really speaking. Yesterday I talked about 1.5 hours for a workshop, giving the solutions to the problems. Probably they may adopt some of them. Today I'm not going to give solutions, I'm going to ask questions. That's what easy for in 15 minutes. So I just going to talk about the kind of challenges that a typical corrosion engineers really have and typical corrosion researchers really have. So I turned my topic like concepts in materials selection and material research for corrosion resistant applications actually. So only the concepts. Before that, I would like to say that the corrosion program at IIT-Bombay was established in 1982. We have a MTech program of 20-25 students per year we intake actually. We have a large number of PhD students, about 20, core faculty members 3, and a lot of associated faculty members. We interact with a lot of industries. Now let's come to the main problem. Well, when you talk about material selection, what do you look for? You don't look for corrosion anywhere here. You look at the properties. A typical engineer or device manufacturer, he looks at mechanical properties, electrical properties, maybe magnetic properties. If you are a chemical engineer, catalytic properties. Where is corrosion here? You don't choose a material because it is corrosion resistant. You choose a material because it has a function to do that. Okay, that is the main important part. The irony of corrosion is simple. A transport engineer looks at magnesium as the lightest material. The corrosion engineer looks at as a sacrificial anode. It corrodes so much. But can I go and tell the transport engineer, oh, don't use magnesium? No. It is the responsibility of the corrosion guy to ensure that magnesium is protected. So the corrosion protection is something we have to do after the selection has been made. That is the task of it. What is that then corrosion means? It's understood very simple, just electron transfer across the interface. Why there's a big fuss about it? Why not we solve the problem so easily, okay? That's a question that people always pose. We don't, I just moved wow, because at the outset corrosion looks very simple. There is a reaction between the material that we talk about, the environment that you have, and then there is a load of different kind that you have, all of them. Dig deeper into that, there are lots of issues involved in materials. So chemistry involved, structure involved, the crystal structure involved, the microstructure involved, even the atomic level things are involved actually. The environment, many differences, a few of them are given here. Chemical species, pH for example, temperature, some of them, okay, and stresses and so on. So it is a complex interface of so many things that happens at the atomic level, at a macro level like stresses that we talk about. So that is where the problem of really finding a solution through an equation becomes so difficult. You wish that there is a constitutive equation that I can do that, but that is really a problem. And look at, again, I told you concepts. Generally speaking, the factors that affecting the corrosion performance in the real life situations, or some of them I listed here, what I ticked are related to material science. we look at materials of construction, it's simply two words. But you go into details, if you look at some of the NACE standards and all, they're simply very gross specifications, 304L, 316L, and so on. But then you dig deeper into it, we have issues there. The codes are never given into the finer points of that. So that's the reason why I need to know more about the materials actually. Specifications, fabrication, you start fabricating. There are different ways of fabricating. The Eiffel Tower was those are riveted now. Now we talk about welding through various like lasers and so on. So range of variation in fabrication makes this material somewhat different. And so the corrosion becomes very different. Again, I told you concepts only. So concepts here for the people working in the field right now. Again, when you talk about materials, there are several issues. The kind of heat treatment you give them, the hardness they have, the tensile properties, many of them to be gone into that in the details. So the industry people have to look at this in details. Unless you look at that in details, just going by the codes, I don't think you can able to mitigate the corrosion problem very satisfactorily. So that's about industry. Let me go into this corrosion research. What are the drivers for corrosion research? It has been talked in the morning. Okay, the drivers which are external for us research. What makes the corrosion engineers to think, to work, are external drivers. These external drivers of energy we talked about a lot in the morning actually. The transportation, infrastructure, fabrication of this actually, and all of them is a flux always. The environment becomes even more important. We talked about coatings which are very good and all. Now these coatings are obsolete. We talk about chromate inhibitors, no. Phosphate inhibitors now say no. Now we talk about inhibitor because the environment becomes a very, very important factors. So these are external drivers for that. Now we also talk about efficient energies and all. Look at the environment we talk about. The typical boilers, thermal power plant talk about steam. Now we talk about coolants which are totally different now. Molten salts we talk about. We talk about lead, bismuth, we talk about and all like that. So these are really a change that is there. Now the question now is another one. What does a corrosion guy drives? The basic research, which is now governed by two things. Today's topic is asset integrity management, prediction and monitoring actually. How can you predict if you don't understand the science of it? The basic research is very, very important. That is to be done. Okay, that I think we have reached some way, but I don't think we have been good enough to make a model, a prediction that can say that, okay, tomorrow the equipment is going to be down, please do it. In that case, AI and ML would help to a certain extent. Okay, I'll come back to this AI ML shortly actually. Okay, but the mechanisms have to be understood. Still we are not there. So the problem is that these questions are being asked people like to us. You've been working on corrosion for a long time, Fontana Center and all. Do we have adequate knowledge to address these issues? Is one of the basic things that people have been asking researchers like that. The problem that happens is that when you do research, even now, you always get surprising results. What you thought is the way corrosion works, they're not working same way like that. I give some examples how it is not working. That means our understanding of the corrosion mechanisms is still lacking because of the reasons which we have been talking about in the morning. Because thermodynamics becomes simple, right? We talked about in the morning because, so you take any engineering metal, right? Magnesium or titanium, aluminum. Only these are being used in the applications. We don't use platinum, we don't use gold and all. That means thermodynamically they are deemed to be corroding. But what makes the difference for them to apply it in the field is the kinetics. But kinetics is not very simple, okay? Because that is something you deal with at multi-scale. We talked about earlier actually. And we talk about multi-environment, and it is stochastic. A flight one day goes through a sea, other day it goes through a volcano. You have something like, calcium, magnesium, aluminum silicate. How? So it's more stochastic thing. Today you have a heat exchanger, having a foulant, tomorrow you don't have it. Can you really talk about heat exchanger? How do you really monitor? That's where monitoring becomes very important. So I'm only talking about the questions that is posed to go into a model that can give you the corrosion rates. Now, the issues that we talked about, let me go into a little more detail. If you talk to an engineer, okay, what are the design criteria? He'll talk about yield strength, may talk about the fracture toughness, okay, talk about the crack growth rates. In the olden days, we talked about these are the numbers used to design the structures. We say that K1SCC is what? Like K1C and K1SCC are the materials property. K1C is a material property and K1SCC is a property related to corrosion. Okay? But that is not right. You see that? It is not environmental specific. I think nuclear persons know that pure water can cause SCC, for example, right? There is no real threshold stress. And there is no real K1SCC values. These are all time-dependent factors, which is very much similar known to metallurgists and the thermal factor, right? Like creep, for example, it is as much of time and as much as the time involved in corrosion. So it is very difficult for us to get an absolute numbers for people to plug into that and say that, oh, I'm going to have a structure which is going to last longer. So this is a time-dependent factor, which essentially means that we need to look at a relationship between how things will change with respect to time. Let me go into some of our results because I don't want to only talk about general thing and see how we enjoyed our work and where we found something very interesting and exciting here. We talk about aircraft. We like to look at, okay, when this aircraft is going to crack, right? The major cracking failure mechanism we talk about are environmental assisted cracking, you see here, okay? But that the life spent in cracking of an aircraft structure, most structures that matter, is only 20%. Remaining 80% of them are different kind of corrosion mechanisms taking place. In this case, it's pitting, some cases IGC and so on and so forth. So the real life of the structure you want to estimate. So look at the events that are occurring before even the so-called what you see as a kind of cracking mechanism here. Okay? So let me just go into this. And we had a lot of publications over the years, and that is not very important. But what I'm going to give you a summary of the results, which we thought it is going to be right, is surprised us. The person who work on metallurgy, they know that a coherent precipitates means it is having more stress corrosion cracking. People develop the alloys actually here. We found not. We did not find that happening. You can have a coherent precipitates, can have very high strength, you can have very high resistance possible to do that. How was it possible? In fact, that is something very beauty that one of our students really found out. But even more interesting was the coherent precipitates which gives you high strength, high resistance to SCC, generates more hydrogen. It's not possible. I mean, you have more hydrogen which is detrimental, but still you can have high resistance to that. So that means the strategy for developing alloy in our understanding is that, oh, you have a precipitates, but can you also control hydrogen evolution on the surface? So the understanding of the SCC mechanism, what we put forward so far, as a radical change that has happened over a time period. So can you now, then we fall back on materials people, look at how do you really design a precipitate, okay? Oh, thank you. So that's the way that we really work on it. So we again go into pitting, for example, right? So pitting is something is done by a student now. How we can look at pit growth, because pit has to stabilize it now. So we look at in situ, how these pits are really happening. Okay, now the time is up. We took up a work recently about advanced ultra supercritical power plant oxidation. It was done first of its kind in India actually here. When you start working on it, another surprise was there. I'll just tell you what it is. Cast alloys are supposed to be prone to more corrosion than the wrought alloys. Look at these polarization curves, some of you guys who have been working on this. The red one is an additively manufactured aluminum, stainless steel. And the black color what you see here is a wrought alloy system. Would you expect a cast alloy will give you more passivation compared to that? No, it is not. It is not the science is wrong, but we are not gone to the science of that actually, okay? That's the point I'm trying to say, okay? So the science is very important for that. Anyway, we start working towards why does really it happening, because of all it boils down to kinetics, right? The kinetics means you look at corrosion at various levels, and that is still lacking in terms of predicting a model that give you what is the corrosion going to be. So I'm going to go forward. We talk about hydrogen, right? I used to tell my students, right, hydrogen gas is not innocuous, no problem. Now the pipelines carrying hydrogen can cause cracking now. Our concept has changed now into that. The storage and transport of this hydrogen high pressure is really a problem. We were having discussion a couple of days back about the engines that use hydrogen. They started testing with hydrogen with the cast iron. I asked them, why did you use cast iron actually? No problem. But decarbonization is the mechanism. It doesn't happen there. So the cast iron used for this, it is not just hydrogen cracking there. It is hydrogen now works in a different manner of taking away the carbon from there, right? So the mechanism that happens in the materials, unless you really understood, then it is very difficult to go in a long way. So again, they started testing out pure hydrogen. I said, don't do it. In fact, people found adding 100 ppm of oxygen to hydrogen can enhance the life of the pipelines. Can you imagine that? Oxygen and this one cannot go together because the mechanism is somewhat different there. So the point I'm trying to say, last point I will tell, and then I close my lecture here. We talk about canisters for storage of nuclear waste. It has lasted for 10,000 years now. People tested this Inconel 22. The best alloy, you put them in 5 molar hydrochloric acid, doesn't corrode. I mean, no pitting, no crevice corrosion. If the alloy is resistance against pitting corrosion and crevice corrosion, I don't think there's any problem at all. But look at the flip side of it. It has a sulfur which is about 0.0, I'm not given here. It's about 0.08 or some 0.008 only. Sulfur is not given here, unfortunately. The sulfur content of this alloy is 0.008. Oh, it's there, sorry, 0.02, only that much. But imagine a case, the metal dissolves and forms a monolayer of sulfur on the surface over the years. What you thought about is not okay. Now that's a problem. So what you envisage the corrosion mechanism happening there, that should be the basis for material development and life protection and so on and so forth. So it is, and this all happened. This all happened. Many of the corrosion failures you see, you know, that happened in nuclear power plant, anywhere else. Recently, it happened in Bay Area, for example. It happened. We are taken by surprises because you don't really. Some of them, of course, not because of want of science, but because want of application of mind, actually. Anyway, so the point I'm trying to say is that these are the things that we have. Coming back to this, the challenges to summarize are: can you develop a science that helps, okay, better materials from first principles? That is our ultimate target of that, actually. Can you monitor infrastructures? Monitoring means you need to understand the science of it. What kind of signals a corrosion gives you and what it really means of that, actually, right? Can you predict the service life of this? Again, it is on this. In my view, there are 2 areas where people have reasonable prediction of corrosion. Is crude oil, where you know the oil chemistry very, very clearly, and use nuclear power field, where nuclear power plants, where you know the water chemistry very clearly. Other cases, still you are lacking far more in terms of really talking about even monitoring is a problem, actually. Okay, so we need to develop a repository of database. This is, I think, wherever I go to industry, ask them, do you have a database in the company? So many failures happen, don't have it. We are not good in writing history, and we continue to do same thing at all, actually. Okay, so this is a very important one. In fact, I know some of the colleagues in China that has sent a national center for database analysis, actually. They have on corrosion only, they do that. Okay, I think this is a most important one. We should do that. And the last point I want to say is that we should nurture the corrosion centers, like any of the centers which have been developed, and so that they take the national task and create new centers so that we are able to reach out to the wider community of engineering fields, actually. So with this, I thank again for the organizer for giving this great opportunity. Thank you very much. Hope I'm not too late.
No, exactly. Thank you very much. So I think I request in case any questions are there. Otherwise, we will go to next speaker. Okay, you have one, yeah.
First sessions of this workshop, we learned that there are some type of inspections, PSIC, in-service inspections are there. So those are recorded in type of some format. So when we talk about this database, is there any framework that has been developed on that framework the data is not available, or the available data is not synced to the framework that we need for developing this?
Okay. See, I'll put it in a little simpler way. Many of the failures in the components happen, many of them happen after 10 years, right? Or 15 years like that, right? Do we really record all this information? I think many people do failure analysis, they do that, okay? Do we really have this? We don't have. But the licensor who gives, I can tell you more openly, the licensor who gives Bechtel or some people, you give the data for them, right? But we don't store it ourselves. So how will you be able to mitigate the corrosion problem? A big oil companies would have much more data, right? Why are we not doing it? So we should have a database. That should be a way of doing it actually. So I would recommend all the companies should have that one, record it actually, and so that you can retrieve this information. Any amount of research in the lab cannot be equated to what you get in the field. What you got for 20 years, especially for corrosion, it is very, very difficult. A corrosion fatigue you do in the lab, it is very difficult to simulate what happens in the ship, for example. Okay, it's very, very difficult to do that. You may have some equations to approximation, but it's not going to be okay. It has to be combined. So that's what I mean. You have to channelize this and get nice data. Of course, setting that at the national level, helping the ML, for example, machine learning and AI is a bigger task to that.
So, sir, in a lighter way, when we talk about the sustainability part for every industry, I think the SEBI registered industry have to disclose the BSR report on their functional and financial aspects. So, when some policy can be
Yeah. Okay. I do not. I can't comment on the legal aspect of it. I'm just asking within the company, how many of us do it? Okay, so that's the thing. That's the thing that we need to do that. Okay. Yeah. Thank you.
Thank you, Professor Raja. Let's give a good. You have.